talking about sources of torque ripple, we can improve on the motor design, and we can improve on the control. And of course, the block diagram we have shown here proposes to make the outer loop significantly faster with an adaptive current reference. Now this simulation would be quite time intensive, so we have not included that, but that is something which can be easily, it'll be quite easily incorporated here. Now, here what we have done is we have put omega reference to both the blocks. So this improves the characteristics of, it's sort of a feed-forward strategy we're using here. Everything else remains the same. All right, so what we have here is now all channel PWM, right? So all channel PWM, this is a schematic, and we are using the same three-phase bridge. The only difference is that we have added element H here in the bottom, H1, H2, H3, to provide us feedback, current feedback. And we also have current sensors in the winding, H4, H5, H6. So we have an option of getting feedback either through the phase currents or through the legs of the inverter. Now, let me just spend a couple of minutes here. Sensing the current in the phase is a whole lot more expensive, and it is the most reliable also, but it's a whole lot more expensive, right? Sensing the current in the inverter leg is much less expensive, right? Now, normally you manage with two sensors because you assume the currents are balanced. So the third current can be calculated by the other two, right? So this is something you can play with, is because you want to replicate through this feedback, you want to replicate your phase current. If you can replicate your phase current through this inverter leg, then you save some money in implementing the control. Now, we have 3 duty cycle inputs here: EA out, A, B, and C. And these 3 duty cycle inputs, we'll see where they come from in a minute. And then we have got, essentially, we use the output of the PWM generator, A top and A bottom, basically because 2 is inverse of A. So we use, so we have saved ourselves some inverters. Is we use output of these PWM generator 1 and 2 for driving top and bottom switch. So it's pretty simple circuit from that standpoint. And all right, so this is our electronic commutator. So this is what we have done in this block. Now this block here is what we call an ABM block. It's the analog behavior model block in PSpice. And what we have done, if you remember, these were the sources we used for
similar one to generate the motor model.
That's right.
The same thing we are using it to the generator.
That's right. So here, what we have let me see if I can So if you can see, I reference is here. So one I reference basically filters through all the voltage sources, right?
Kind of same B reference, whichever we see it here. I reference, instead of voltage we are seeing the current.
That's right. That's right. That's right. This is the basically current controlled. Right. We're controlling the current. That's correct. And let me just verify one thing here. So you have similar delays: delay 1, delay 2, delay 3, delay 4, delay 5, delay 6. So we go to, and I want to explain this particular function here, where this is what we do is we take this. Now this waveform here goes plus and minus. Okay. So when we have this here, this goes plus and minus. Now by using this function here, we are able to generate. This is I reference A now is a duty cycle command. Okay, and this goes from 0 to 1. So what we have done is normalized. So the formula is all right. So what we're trying to do is take the signal, which is Vn, is what it says, and we are going to divide that, I believe, by this says we're doing this Vn plus Imax divided by 2 times Imax. So, and this is your I reference. You can call it, this is I reference A. Okay. And Imax, for example, in this case is 10 amps. And I reference A we said was 5 amps. So this basically 5 plus 10 divided by 20 gives you about 0.75. So that's a duty cycle command which goes into. So here, basically, when you ask for Imax, your duty cycle becomes 1. Right? So that's the maximum current you can deliver through your inverter. So that's a parameter Imax. So all we're doing here is, for the current commands, we're normalizing with this model, analog behavior model. Does that make sense? And I'm just going to make that. Okay, so here the current, which is the current we are asking for is trapezoidal in nature, right? So you have got so these two waveforms at the bottom. Essentially, they generate a current which is like this. And we take that current, and this is, let's say, if I reference is 5 amps. So this is evaluated as 5 amps and minus 5 amps. And by adding this term, we essentially are shifting this reference to give us. So this becomes a duty cycle command. We can call it DA. Okay, so it's shifted because our PWM will only take duty cycle values from 0 to 1. So we take this current from 5 to minus 5 amps, shift it by the maximum current, and then feed it to the duty cycle DA. Okay, so which is, you have to do that anyhow if you're using a DSP because you can't handle negative currents at all. So it's a level shifting you're doing. And here is a simple PI loop. We basically take the feedback. Now when you take the feedback, you also normalize it. So if you look at the feedback, same formula you use for the feedback here. So this is the feedback coming in. and you have got I reference A goes here, feedback goes here, you have simple KP, KI loop, and that basically becomes your final duty cycle value. EA out A, EA out B, EA out C. Okay, so it simplifies your. And now what we did was we were tired of writing the long equations for power. So we basically make blocks, 3 blocks. So this one is power for phase A, power for phase B, power for phase C. And then we add them up to get P out. So we'll be able to just plot P out and get it. Okay, so here you can see that we have added IREF. Now IREF is a part of the parameter file, is equal to 5. Imax is 10. We have input voltage of 36 volts. And then we have still the same motor. And let's see, and everything else pretty much remains the same except that duty cycle, max duty cycle is now 0.95 and min is 0.05. And we have a KP set at 25 and KI set at 10. Okay, those are the values. So, and these are the currents we got. Now these are not the prettiest currents because they have this ringing here. But as you can see, if you look on the green one, it tries to go up to 5 amps. So it starts. So you're able to follow, but you have got some doopsie-doo going on here, right here. You have got these nice rings on the current. Okay. Now this is because now we have moved from square wave current to trapezoidal current, and the back EMF is square. This is the power output, and here is the harmonics of the phase A current. So this harmonic here is really the rotational frequency harmonic, and then you have got these harmonics. It's a multiple of the. Let's see if I can blow it up. So this one is your rotational frequency, and this one is 6 times the rotational frequency, that harmonic. And this one is essentially, again, a multiple of the rotational frequency.
You have the speed versus time for this particular?
No, we still are not doing speed. This is still constant speed operation.
But you already have
Put that in the loop.
We have not. That would have been quite difficult to demonstrate here because it's taken some time.
Whatever results we are seeing, it's not for a.
No, it's not a closed system. No.
this PI control block is not in the circuit?
It is. Yeah, that PI block is in the circuit. We'll see that in a second.
Another PI block voltage.
So you mean to say about the inner one? The inner current regulator is in picture.
That's right.
So the outer speed control is not in picture.
Is on. This is the power output, and let's do demonstration 4. motor model remains the same. And this is how we generate the current references. So all we're doing here is normalizing it. See it better, how it is done. Just take input from here. These inputs are in series, so take this input plus Imax divided by 2 times Imax. That's how you do it. Okay. And then this is a PI. So we're using 3 PIs, and that's the implementation. We take the feedback, we normalize it, and then we feed it into the PI, and then we get the duty cycle out. All right, so, and then this is the block for power calculation. So we take the phase voltages and multiply by the current to get the phase the power. So this is our then we add PVPC to get P out. And the simulation settings. So we have up to 23 milliseconds, 6 milliseconds start time, 5 microsecond maximum step size. So we're going to run this. Let me just check one thing, how the back end is. Okay, in this particular example, back EMF is also trapezoidal. So you have a trapezoidal back EMF and trapezoidal current.
Physically giving the reference signal here,
Through the parameter file.
just inputting it.
Yes.
You're just telling that give me 5 amps.
That's right. That's right. So this one becomes a little bit more time intensive because we have got now a closed loop. We have not only incorporated all channel PWM, we also incorporated a closed loop system.
So the speed then is a function of time then,
Constant speed.
constant speed. So the closed loop is for what?
For the currents.
For the current.
Yeah.
How did you determine the value as 10?
Arbitrary.
Random values here.
So you, for example, when you're designing an inverter, right, you design an inverter for 60 amps, but you may limit internally to 40 amps. So Imax is sort of an arbitrary. Now, we should have paid more attention to the motor characteristics here. Maybe that would have given us better results in terms of current speed, because this is not a high power motor, this is a low power motor. So one interesting experiment to do would be if we have I reference is 2 amps, perhaps the current shapes will be a little better than what it is today.
Because you are shifting your limit very high.
Yeah. It seems to hold the 5 amps, seems to be able to control the 5 amps quite effectively. But see, the simulation time takes quite a bit when you're trying to do closed loop. So this is the current waveform for IL. So you have got some it's following the top. Now you can see that it's below 5 amps here, and here it is above 5 amps. So there is some optimization required for KP and KI here. It's not fully optimized for system here. And then if I add other traces, okay. So that's how you're looking at it. Now this is you can tell it's not a very well optimized system. Number one is that on the top, this width is bigger than this width. So obviously you have got some errors in your control loop which need to be corrected. And so that's one thing which we need to correct in this loop. What else we want to see? So this is all channel PWM at all times. So let's look at some waveforms. Input power will be one which we should look at. So let's look at input power. So we're going to do so this is our input power. And do an FFT on this, and we go to